I'm going to show us a simulation from the University of Colorado, which demonstrates how these graphs of position and velocity look like in an angular problem, where let's say we're graphing the location of a little ladybug that's sitting on a merry-go-round. We can graph the angle that this ladybug makes, where right now it's an angle of 0, because if we say the origin is the center of the merry-go-round, and this ray that goes out toward the ladybug then makes an angle 0 with our coordinate system, then when the ladybug rotates up to being over here, that's at an angle of 90 degrees, or when it rotates to be over here, it's at 180 degrees, and so on. That's going to be plotting its angular position. And to get a sense of why it is that the angular coordinates are so useful for an object that's just sitting at some constant radius, we can also graph its x and y locations. In other words, if this is x is 0 and y is 0 right here, and this is the y direction and this is the x direction, notice as this thing is moving, what happens when to the graphs of x versus y. Being at this location where it is right now, it happens to have an x value position, but it has a y of 0. And I'll just play with the angular velocity as we go along. So we'll start this thing at 0 angular velocity, and watch what happens to the graphs. Theta is not changing, and the x and y coordinates are not changing. So now I'll start it moving with some angular velocity. And notice the angular velocity omega jumped up at that moment. The angle theta is changing at that moment, and the x and y coordinates are starting to evolve. When the bug comes around being right about here again, that's when x is 0. When the bug is up here toward the top, or down here toward the bottom, that's when y is 0. Let's make it go in the opposite direction for a little while. Notice at that point, omega dropped down from being a plus 1 to a minus 1, and theta started decreasing in magnitude again. Let's just look again at what I just did. Theta is constant because omega is 0. Theta is now starting to increase linearly because omega is plus 1. And x and y are doing this complicated thing where at various times, here's y of 0 corresponding to the bug being down at the bottom. Here's x of 0 corresponding to the bug being over here to the side. Here's y of 0 again, corresponding to the bug being at the top. These graphs look like sine and cosines. Not surprising, because if we think about the bug being along a hypotenuse of a triangle, the hypotenuse always has length 1. But the sides of the triangle always have a length cosine and sine of theta. And theta is just changing nice and linearly, so these things are going to become sine and cosine graphs. They're very complicated looking and probably not worth us keeping track of when you could have the opportunity of just having a linearly increasing graph like this or a linearly decreasing graph like that, responding to a constant velocity. So this is one really good demonstration of why it is we use these angular coordinates so much, rather than having to pay attention to linear coordinates all the time. They are, of course, mathematically related to one another. X is just r cosine theta, and y is just r sine theta. So we could work in either way, but since there's really one part of this problem that's not changing, that's the radius location, it's just so much easier to keep track of theta.